Hi everyone, this is a lesson about volumes of solids using cross sections. So the basic idea is that we can stack two-dimensional cross sections on top of or next to each other to create a 3D figure. And this is how we're going to think about a 3D object to calculate its exact volume. So think of a roll of salami, for example, that looks like this. You can slice the salami and make up this roll by just putting all of these slices together. So each salami slice would have an area of the cross section, and then its width, we might call it dx. And if we integrated the volume of each slice, this would be the volume of each slice. If we integrated it, integral is an adder, so the integral will just add up all of the slices and you will get the total volume. So this is the basic idea that we're using here. And in general, we are using an integral to add up or to accumulate all the cross-section volumes, and thereby we can find the total volume of the 3D figure. So we think of S as a solid lying between x equals A and x equals B. A of x is the area of a moving cross-section obtained by slicing through S perpendicular to the x-axis. So in these first few examples, our solid is sitting sort of like this, centered on the x-axis, going from x equals A to x equals B, and then the cross-section might be at different places. And then we're just integrating the A of x dx from A to B to get the total volume of the solid. This is the total volume of S, which is the solid. You integrate from A to B, and here is your cross-section volume. And A is your cross-section area. So this is the basic idea. Now let's see how this works with a few examples. So area formulas, you need to know them. I'm not going to go over them here, but we will cover them as we do the examples. So this first example says the base of a solid S is a circle of radius 1. For this solid, the cross-sections are cross-sections perpendicular to the x-axis are squares. Find the volume of the solid. So we've got a situation where the base of the solid is a circle. This circle is sitting in the xy plane and it has radius 1. As you know, the equation for a circle is x squared plus y squared equals r squared. In this case, r is 1. So y, the top of the circle, y squared is 1 minus x squared. And we've talked about before how that means y equals the positive square root is the top of the circle, and y equals the negative square root is the bottom of the circle. So this is my base, and then on top of this I'm building a solid which has cross sections that have a square shape. So in other words, what that means is I'm taking for example, this as one side of my square, and then the square would go up like that. And, there would be this, I'm just rotating it a little so you can visualize this a little better, but there are squares throughout this solid, and they all look like this. Each of them has a base in the yellow region, and then the square goes up from there. The teeny tiny ones on the end will have, they look like this. And I encourage you to play with the GeoGebra app that I used in class so that you can visualize these better. So now when we talk about the volume of the solid, we're going to need to find this length of the base that's lying on the yellow region. So the length of the square side is going to be the top of the circle, which is 1 minus x squared, minus the bottom of the circle. That's like a y high minus y low. It's this y number minus this y number at any given x value, right? So that is going to come out to be like this. So that'll become a 1 plus square root of 1 minus x squared plus square root of 1 minus x squared, which I can simplify to 2 times the square root of 1 minus x squared. So that is the length of the side of the square. So the area of the square is L squared, right? That's the area of any square. So I then just square this and I get 4 times 1 minus x squared. And now that's what I need to put into my volume equation. The volume equation was back here, if you remember. It's the integral from a to b of the area dx. So I go integral. Now the a and the b are these two ends of my circle, right? Because that's the x span. That's the place where my base is sitting from x equals -1 to x equals 1. And then I just integrate this area equation, 4 times 1 minus x squared dx. So from here, you either have math 9, in other words, you do a calculator problem, or if you don't, you have to do an antiderivative and find this answer. So when you're doing this by hand, you want to use symmetry, and you want to realize that since this solid is perfectly symmetrical on both sides, you can just go 2 times the integral from 0 to 1 of the 4 minus 4x squared, right? I can change this and just double the answer. And then I would get 2 times 4x minus 4x cubed. Just take this through to an answer from 0 to 1. And that would be 2 times 4 minus 4 thirds, which is 2 times 8 thirds, or 16 thirds, which is 5.3333. If you're using a calculator, give me the answer to 4 decimal places. Okay, the next one is exactly the same problem, except, so I still have this base, which is in the x-axis. It's a circle from -1 to 1. I still have this thing, and I'm now still making cross sections perpendicular. By the way, that means that the base is perpendicular to the x-axis. Cross sections perpendicular to the x-axis. That means when you draw the side that's lying in the base, it has to be a right angle to the x-axis. But the shape is equilateral triangles, which means that my solid, is made up of slices that look like this, okay? And at the very end, I'll have like teeny triangles, and it'll go through the entire yellow region. And these are all 3 same length because it's an equilateral triangle. So that length of the base is still exactly what we talked about before. It's the y at the top of the circle minus the y at the bottom. So that will again come out to be 2 times the square root of 1 minus x squared, just like it did in the last example. The equilateral triangle, an equilateral triangle of side L, L, and L, the formula for the area is rad 3 over 4 L squared. You're going to have to memorize that. It's a nice exercise to go and think about why that is the case. But you can just memorize this and now use it here to say the area then is rad 3 over 4, and we put the L from there and square it. So the 4s, it's going to be rad 3 over 4 times 4, and then the square root and the square are going to cancel. So we'll end up with rad 3 times 1 minus x squared, and we'll take this into the volume integral, integrating from -1 to 1, and it would be, this volume integral would be rad 3 minus rad 3x squared. I'm distributing this. Dx. Again, it's a symmetric situation, so if you're doing it manually, that is without a calculator, I would use symmetry and go from 0 to 1. That will minimize chances of an error. But we're also practicing doing math 9 and getting the right answers. So this particular answer would come out to be 2.3094. Okay, the next several problems are similar, except that the base is just defined by 2 equations, x plus 1 and x squared minus 1. And the question is worded like this: find the volume of the solid whose base is bounded by y is equal to x plus 1 and x squared minus 1. with the indicated shape of cross sections taken perpendicular to the x-axis. So when you are just given two equations for the base, your first step is going to be to graph those two equations. And so you'd come up with something like this. We've got a parabola and a line. So here's my parabola, x squared minus 1, and then I have my line, x plus 1. So the base is the region bounded by these two graphs. So very often, actually, the first part of the question will be find the area of this region. In this problem, though, they jump straight to the volume question, and we're told that we have cross sections, again, perpendicular to the x-axis, so they're lying like that. And then we are told the shape, so first a square. So that means, my cross section looks like this, and I just first need to write my L equation and then my A equation. So my L equation for the length, L being the length of this side of the base that lies, the side of the square that lies on the base, that's going to be L is equal to the top equation, y high. This is like our y high because it's higher than the other one, y low. So it's y high minus y low. And you want to simplify this into negative x squared plus x plus 2. And now we'll take it into an area formula. So area, you're going to look at the shape. This is a square. So we'll just square that. The area will be the length squared. Okay, then we do the volume integral. The volume will be the integral from. Now the integration limits are going to be where the two graphs intersect. So for that, you should just set the two equations equal and solve. And when you do that, you're going to get x minus 2, x plus 1. You might get different equations at this stage. And if you have a calculator, you can solve these with the solver or by setting up, these two equations as two y's and finding the intersection point. Anyway, you get 2 and negative 1. Those are going to be your limits on the integral. So this is going to go from negative 2 to pause. Sorry, I think I did that wrong. 2 and negative 1. So negative 1, the lower one, and then the upper one. And then in here goes this a of x that we just found, dx. And now this is a moment for Math 9, and practice getting the right numbers when you put in these into your calculator. You should be getting 8.1000 for that first problem. The second one, now these ones, B, C, D, and E, are just changing the shape of the cross section. So the base is the same. It's that same x plus 1 and x squared minus 1, that same yellow region, except the cross section is a rectangle of height 0.5x plus 1. So the situation looks the same in terms of the base. It just looks like this. We've got this same base. Oops. Let me just color that in yellow. And now, though, we're putting up rectangles. And the rectangles look like the same, this length, which will be x plus 1 minus x squared minus 1. And the height is this equation, right? So they're literally giving us a height equation here. So we know that height. And then this is our situation. We're putting rectangles like that throughout the base. So the rectangle length is going to be x plus 1 minus x squared minus 1, the same exact thing as before. So we get negative x squared plus x plus 2. And then the area will be that times the height, because it's a rectangle. So length times width makes area. So I will take this equation and put it into my volume integral for v is equal to integral from negative 1 to 2 of negative x squared plus x plus 2 times 0.5x plus 1 dx. And answer here is going to come out to be 5.625. Okay, then we have semicircles. So for the semicircles, we'll have the same length for the base side, which is just that, and this will be now the diameter of your semicircle. So the semicircles are sitting like that. So the diameter, so I just want to draw the region, is looking the same. So we're doing something like this. This yellow region is still the same, but each of the y high minus y low, which is this thing, the length, is a diameter. So we've got to divide that by 2 to get the radius of these semicircles. So the radius of a semicircle is half of the diameter. So then my radius is going to be negative x squared plus x plus 2 all over 2. My area is going to be pi times the radius all squared, and my volume will be integrating this area, so put that into your integral dx, and final answer here should come out to be, and it's a semicircle, so not only this right here is pi r squared, that would be the whole circle. I want pi r squared divided by 2 because it's a semicircle. So let me just write this out here, make sure we are understanding what goes into the integral. So into the integral, you would put pi over 2, and then this whole thing squared dx. And when you do all of that, you should come out with an answer 3.1808. Please practice doing Math 9 and getting these answers. Equilateral triangle. So for equilateral triangle, your length will be the same. That's the length of the side of the triangle in the yellow region. Area is going to be rad 3 over 4 times length squared. That's the area of an equilateral triangle. Volume integral will be negative 1 to 2 of rad 3 over 4 negative x squared plus x plus 2 all squared. Be super careful when you put these into your calculator, and you're going to come out with this answer. Isosceles triangle is the next one. Let me flip to the next slide. Okay, so I want to talk about isosceles triangles a little bit. There are a couple of situations that can go on with an isosceles triangle. So let me redraw our region. Our region looks something like this, and we are still just putting things up onto this base of this. The solid base is in yellow, and then an isosceles right triangle with the leg on a base. So let me just explain the vocab here. Isosceles means that two sides are equal. Right means that those two equal sides are at a right angle to each other. And in a triangle with a right angle, these are called legs, and this is called the hypotenuse. So in other words, these triangles are looking like this. Here's a leg, here's another leg straight up, and then there's the hypotenuse. Leg, straight up, hypotenuse. This is this situation. We're going to do another situation in a minute. But for this situation, if I call this leg L, then the area, right, 1/2 base times height just comes out to be 1/2 L squared. The L is the same as before. It's x plus 1 minus x squared minus 1, right, which boiled down to this. And so we'll just say area now is going to be 1/2 of that thing all squared. And volume will be then the integral, same limits of integration, negative 1 to 2 of that guy, this area, dx. And this is going to come out to be 4.0500. Okay. So once again, make sure that you know how to do Math 9 and actually get this correct answer out of your calculator. Okay, now in this situation, the length that we had lying in the base, right, was a leg of the isosceles right triangle. So what we knew was this leg length. So there can be another situation where the question says it's an isosceles right triangle with the hypotenuse in the base, right? And that would be this situation where the right angle is actually sticking up in the sky. And what we know, the x plus 1 minus x squared minus 1, our L, is actually the hypotenuse. So let me call it an H for hypotenuse, right? We know the hypotenuse is this, then it would be the same equation, but it's no longer a leg length. It's the length of the side in the base, in other words, in the yellow part of the solid, but it is a hypotenuse of a triangle. So if you have that situation, you use the formula that the hypotenuse and the area for an isosceles triangle are related by A is equal to H squared over 4. So if you use that, and the reason is because if you have a right angle here, this is 45 and this is 45. So then if you say sine of 45 is equal to the leg divided by the hypotenuse, then the leg is going to be equal to H over rad 2. And each of the legs is the same, so then when you do area, 1/2 of the legs multiplied, you're going to end up with H squared over 4, right? So this is the area formula if you have this hypotenuse lying on the base, and the integral would be then from -1 to 1, H squared, so that thing squared, over 4 dx. This will be our volume integral. And you can check this out and make sure, actually, I don't know what the answer is to this. Give me 1 second. Oh, let me fix this upper limit. It was -1 to 2, and I'm putting it into the calculator just now. And I'm getting an answer of 2.02500. Yeah, 2.025. So you want to be pretty careful here when you put this into the calculator. You need these parentheses here. You need to divide the integrand by 4, or you can first do the integral and then divide everything by 4. Whatever you do, you have to be pretty careful. So I would really practice, again, using Math 9 and getting these answers correctly. Let me Hi, folks. I just want to go over this example 3 again very quickly here. So example 3 said, let R be a region bounded by the graphs of e to the x and x cubed and the y-axis, right? So that's the region right here. E to the x is in blue, x cubed is in green, and the y-axis, is right here. We could do it in red, right? So that leaves me with that yellow region. And we calculated the area of that region, and for that calculation, we're really just doing our Riemann rectangles with the y high being e to the x and the y low being x cubed. And so in my integral, I put e to the x minus x cubed. I'm integrating with respect to x, and x starts here at x equals 0, and it's going to end here at x equals 1.8571839. We got these two intersection points out of the, that's one intersection point, the x value and the y value. We got that out of our calculator by doing second trace, and then, of course, the intersect function. Okay, so then the next part said, find the volume of the solid with base on the region R, which is that yellow region, and cross sections perpendicular to the x-axis. So now remember, the cross sections perpendicular to the x-axis, what that means is that the cross sections are like this, okay, just like our y high minus y low, and the cross sections are triangles. So we have a triangle at each of these spots, right? We are erecting it so that it goes up this way, and then there'd be another one here, right? And so our base of the triangle is that same y high minus y low. So here's the base of the triangle, and then the height of the triangle is 3 times the base, right? And that's given to us in the question. And that's how we end up with this formula for the area. 1/2 of e to the x minus x cubed times 3 times e to the x minus x cubed. We put that whole area into the integral, right? And we're integrating again with respect to x, and our integral starts here at x equals 0 and goes all the way until x is equal to 1.8571839. Okay, for the last part, things are a little bit different, and this is what I wanted to explain better. We have for part C, a volume of the solid with base on the region R, so still on that yellow region, but cross sections are perpendicular to the y-axis. The cross sections are rectangles, and they have a height 6 times the length of the base, right? So if we are thinking of a random rectangle on this base, if your cross sections are perpendicular to the y-axis, that means the rectangle is sitting like this. This is what we mean by perpendicular to the y-axis. We're going in that direction for our rectangle side that lies on the base, and then we're going up, 6 times as high. So it's going to be a tall, skinny thing like that, and that is your rectangle, okay? So if we're looking to write an equation for the base of this rectangle, then we need an equation for this distance right here, okay? Now, if you look at this picture, you can see that things change at y is equal to 1, right? Here's y is equal to 1. If I'm above y is equal to 1, then I can write this length of my rectangle side as x right, which is on this green curve, minus x left, which is on the blue curve, right? So x right on the green curve is the curve y is equal to x cubed. So x on that curve is equal to y to the 1/3. We could just rewrite that as x is equal to y to the 1/3, and that would be the x right that we need. Similarly, on the other side, right, if y is equal to e to the x on the blue curve, then x is equal to ln y, right? So our x left here is equal to ln y. So the length of my rectangle is y to the 1/3 minus ln y. This is the rectangle side that's lying on the base. And then I would have to multiply by 6 times that same length, and that would give me the area of this blue rectangle, for example, okay? Now, that's true for any y values that are greater than 1. However, if you are down here, at say a half or something, y equals a half here, then your x right is still y to the 1/3, but your x left, the boundary is now the y-axis, right? The boundary is not the e to the x graph, the boundary is the y-axis. So you would get an equation down for less than y is less than 1. Your equation will look like y to the 1/3 minus 0 for this distance right here, because on this side it's y to the 1/3, on this side x is equal to 0. And then, of course, you'd have to multiply by 6 times that again, right? And that's just the rectangle height. So here's your length and your height, just like we had before, right? But the length is different now. This was our length and height before. Okay, so that's what we're going to put into the integral. We're going to split our integral into 2 pieces. First, we will integrate from 0 to 1. And for that stretch, I say y to the 1/3 minus 0 times 6 times y to the 1/3 minus 0. This is my a of y, and I'm integrating with respect to y. And then I go all the way from here up to here, up all the way to here, right? And that's this y value for my second integral, up to 6.4056721, which we got out of the intersection point, right? And for there, the right is y to the 1/3, and the left is ln y, and so this now is my a of y, right? Notice that for both of these integrals, there's no x inside the integral. It's all written with respect to y. There's all y's in here, and y's in here, and the variable of integration is dy. Okay, when you put this into the calculator, of course, we only have an x button on our calculator, right? So the variable will be called x in the calculator, but these are the equations that we would put in. You can simplify this guy down a little bit and pull the 6 out and make this y to the 2/3. Here also you can pull out the 6 and make this y to the 1/3 minus ln y, the quantity squared. Put that carefully into the calculator and you get this answer, 8.9177. Okay, I want to do one last example for you. The region R in the plane bounded by the graph of f of x is equal to 4 cosine x divided by 2, bounded above by the graph of f of x equals 4 cosine x over 2, below by the graph of e to the x, and on the left by the y-axis, right, is the base of a solid. So that's this region. And obviously you're plotting, this is a calculator active problem. You plot the graphs in the calculator, you also find the intersection point, and that's what it looks like. For this solid, the cross sections perpendicular to the x-axis, right? So my cross sections are going this way, perpendicular to the x-axis, are semicircles with diameters extending from f of x to g of x, right? So that means that I'm putting up semicircles like this. The diameter is like that, and then you got a semicircle like that, and another one like that, and a semicircle, you know, and you are going all the way from one end of the region down to this point, right? So smaller and smaller and smaller semicircles as you come in here. And that's what our solid is going to be made up of. And we are just trying to find the volume. So pretty simple, honestly, because our diameter of the semicircle is equal to y high 4 cosine x over 2 minus y low, which is e to the x. That's the diameter. If I want the radius, right, which I'm going to need for my area, that's going to be this diameter divided by 2, all divided by 2, okay? And the face of these semicircles, right, this area here, is going to be equal to pi r squared. The area for any one of those is pi r squared divided by 2. So this is my r. So that's going to become pi 4 cosine x over 2 minus e to the x all over 2. That whole thing squared, and then that divided by 2. Okay? So that's the only thing. I mean, you could put this in exactly like that into your calculator. Maybe that's your safest bet, because you might make a mistake if you try to simplify it. And anyway, the volume is going to be the integral starting at 0 and going until this x value, 1.1957721. This a of x, notice this area is a function of x, right? Because depending on where you are, the semicircle is bigger or smaller. This whole thing is our a of x, so that goes in here. So I'll write it like this, pi over 2, and then that's this pi over 2, right? And then that whole equation like this squared, right? And don't forget to square this 2 on the bottom as well. And it's integrated dx. So the idea is that each of these has a thickness. This thickness like this is dx. So each of these is a little bit of volume. This is now a little volume, and we are adding up. The integral adds up all the little volumes. So you have to just put that in carefully into your calculator, and you will get out an answer of 1.9, oops, not 1.1, 1.937.